This lecture is part of a series of online lectures about rings and modules and will be about resultants. So for motivation, I'll start by recalling some things from the previous lecture. What we were doing is we were looking at a polynomial x to the n minus e1 x to the n minus 1 plus e2 x to the n minus 2 and so on, which had roots alpha 1, alpha 2 up to alpha n. And we showed that e1, e2 and so on generated the ring of all symmetric polynomials in the alpha I. And there's one particularly important symmetric polynomial in the roots alpha I, which is the product over I not equal to j of alpha I minus alpha j, which is called the discriminant of the polynomial, or at least up to sign. It's always a bit difficult pinning down the sign of this for a reason I'll explain a bit later. So the discriminant is so called because it discriminates between polynomials that have multiple roots and polynomials that don't. You see that the discriminant vanishes exactly when this polynomial has a repeated root. In general, anything ending in the word ant is an example of an invariant. So Sylvester coined a lot of words like these. So discriminant and determinant is another obvious example, and resultant is a third example. Anyway, so we want to know, when does a polynomial f of x have multiple roots? Well, f has multiple roots over an algebraically closed field is equivalent to saying that f and its derivative have a root in common. This is not very difficult to see. For example, if f of x is equal to x minus alpha squared times g of x, then its derivative is equal to 2x minus alpha times g plus x minus alpha squared g prime, so it's got a factor of x minus alpha. And conversely, you can see that if f and f prime have a root in common, then this must actually be a multiple root. So we want to know when these two polynomials have a root in common. Before going on, I should just add a warning that characteristic p gets a little bit weird as usual. For example, if we take f of x equals x to the p minus a, then its derivative f of x is actually equal to 0. So a polynomial can actually divide its derivative in characteristic p. I mean, you might think it never can because the derivative has smaller order, but sometimes it's actually 0. Notice that in this case, f and its derivative certainly have lots of roots in common because the derivative is 0. And in fact, this polynomial does have a very highly repeated root in characteristic 0 because this is equal to x minus the pth root of alpha to the power of p. So although this works in characteristic p, it gives slightly unexpected results at times. So we now have the problem, when do f and f prime have a common root? Well, actually, we're going to answer a more general question, which is when do f and g have a common root? Whenever f and g are any two polynomials over, as usual, an algebraically closed field. And there's a simple answer to this. If f and g have a common root x minus alpha, so suppose x minus alpha divides f and g, then we see that f of x, p of x equals g of x times q of x, where p of x is equal to g over x minus alpha, and q is equal to f over x minus alpha. And we also notice that the degree of p is going to be less than the degree of g, and the degree of q is going to be less than the degree of f. if we didn't have this condition about the degrees being less, this would be completely trivial because we would just take P equals G and Q equals F. So we can find P and Q of smaller degrees. And now if we sort of think about it a bit, we see this equation is really a set of linear equations in the coefficients of P and Q. And the coefficients of these linear equations are just something to do with the coefficients of F and G. So we've got to solve a set of homogeneous linear equations and find a non-zero solution. Well, we know that a set of linear equations with the same number of variables as the number of equations has a non-zero solution if and only if the some determinant is equal to 0, where this determinant is going to be something to do with the coefficients of the linear equation. So we can so we have reduced the condition that f and g have a common root to some determinant being equal to 0. Now we need to sit down and calculate this determinant. And it's not very difficult to do. What we do is we get the Sylvester determinant, or the Sylvester matrix rather, which looks like this. So I first of all need to tell you what the coefficients of f and g are. So let's put f of x equals am x to the m plus all the way down to a0, and let's put g of x equals bn x to the n plus all the way down to b0. And then the matrix giving all the linear equations like this turns out to look like this. First of all, we write down the coefficients of f, am minus 1 down to a0, and then we put in a few zeros, and I'll tell you how many in a moment. And then we have 0 am down to a1, a0, and then a few zeros, and we keep going like this until we get 0, 0, 0, and then we have am going down to a0. And the number of rows here is going to be n rows. And then we do the same for the b's. So we put the b's down here. We have bn down to b0 and then some zeros. And the number of rows here will be 0. And then we have 0 bn, 0, b1, b0, 0, and so on. And we go all the way down to 0, 0, 0, bn down to b0. So we've got this big matrix, and we just take its determinant, and the vanishing of this determinant is the condition for f and g to have a common 0, and this determinant is called the resultant. Actually, we've got to be a little bit careful because we're tacitly assuming that am is non-zero and bn is non-zero. If the leading coefficients of f and g are 0, then this determinant automatically vanishes even if f and g have no root in common. So what you do is you say that am equals 0 or bn equals 0 means that f or g have a root at infinity, whatever that means. And then you can say the determinant vanishes exactly when f and g have a common root, except this root might be at infinity, meaning am and bn both vanish. Well, as you can imagine, working out this determinant is actually a bit of a mess, except in a few small cases. I've got some pictures of it from Salmon's 19th century algebra textbook. Let me just magnify this a bit so you can see. So down here we have the resultant of degree 2 and a degree 5 polynomial. Down here we have the resultant of 2 cubics. You see it's already going on for about half a page and looks like a bit of a mess. The resultant of 2 degree 4 polynomials is already going on for this page and most of the next page. So the resultant of 2 degree 4 polynomials takes an entire page to write out in detail. now we get back to the condition for f and its derivative to have a common zero. So the the discriminant of f is equal to the resultant of f and f prime, at least up to a constant. So all these matrices are defined up to a constant, and the constant is actually quite hard to pin down sometimes, especially getting the sign of it right is a little bit tricky, as I'll mention in a moment. So let's do an example of this explicitly. So let's take f to be a cubic, and I'm going to take it to be x cubed plus bx plus c. And you see I'm omitting the coefficient of x squared. You can get rid of the coefficient of x squared just by adding a constant to x, so we aren't losing much generality. And now the derivative of f is going to be 3x squared plus b. So we write down the Sylvester matrix, and that's not too hard. What we do is we write down the coefficients of f, which go 1, 0, b, c, 0, and then we write down the coefficients of f again, only we shift them a bit. And then we write down the coefficients of the next polynomial, which are its derivatives. So we get 3, 0, b, 0, 0, 0, 3, 0, b, 0, and 0, 0, 3, 0, b. So this is now the discriminant. This determinant is now the discriminant of this, and it's a 5 by 5 determinant, but it's not too bad working it out because most of the entries are 0. And what we find is this is 4b cubed plus 27c squared, except up to sign, because the sign is a bit difficult to pin down. You know, it's not really clear that the sign is even terribly well defined, because if we swap two rows of this matrix, we're going to change the sign of it. So maybe if we'd put these polynomials in a different order, it might change the sign or something. So we've got, this needs more work. So how do we pin down the sign? Well, the easy way to pin down the sign we evaluate both sides for an explicit polynomial. So both sides meaning on one side we have plus or minus 4b cubed plus 27c squared, and on the other side we have the product over alpha I minus alpha j all squared, or maybe this is for I not equal to j. So for I less than j, that would be the square of the discriminant. So an easy polynomial to do this on is just x cubed minus 1, because the roots in this case are roots of unity, and we don't really need to evaluate this product explicitly. All we need is the sign, and we notice that this thing actually has, so the sign is going to be less than 0. It's definitely a negative number, and so we must actually have the minus sign here. We must have minus 4b cubed minus 27c squared, at least if we're using this as the discriminant. So we've now found the discriminant of the polynomial x cubed plus bx plus c is minus 4b cubed minus 27c squared. And we'll give a couple of quick examples of using this. For instance, in number theory, a basic invariant of an algebraic number field is its discriminant, which turns out to be more or less the discriminant of a polynomial giving a generator. It's not quite the same, but it can differ from it by squares or something, but you can find out about that in a number theory course. So let's take our polynomial to be x cubed plus x plus 1. So if alpha is a root and we want the discriminant of q of alpha, the discriminant will be minus 4 times 1 cubed minus 27 times 1 squared, which is minus 31. So it's easy to work out. In algebraic geometry, you might want to know, when is y squared equals x cubed plus bx plus c an elliptic curve? Well, it's an elliptic curve provided it's non-singular, and in algebraic geometry you find this is non-singular as long as this doesn't have any repeated roots. So it's an elliptic curve when minus 4b cubed minus 27c squared is equal to is not equal to 0. By the way, I should just show you some more examples of discriminants for higher degree polynomials from Salmon's book. So I think here we have the discriminant of a cubic, except here he's given the cubic with without assuming one of the coefficients is 0, so you can see it's slightly more complicated. And here we have the discriminant of a quartic, so it's a couple of lines long. It's not too bad, but you probably wouldn't want to work that out by hand. Next we can ask, what is the geometric meaning of a resultant? Well, suppose f and g are homogeneous polynomials in y and z, in two variables y and z, with coefficients in, say, over a field, with coefficients that are polynomials in x1 up to xn. So we can think of f and g as defining hypersurfaces on n-dimensional affine space times a copy of P1, because a homogeneous polynomial in two variables can really be thought of as zeros can be thought of as lying in one-dimensional projective space. And the resultant of f and g basically tells you when do f and g have a common 0 in P1. And if you think about it a bit, this means that if you take the hypersurfaces HF and HG, what you're looking at is the intersection HF and HG, and then you projected to AN. So this is what the resultant is telling you. You take the intersection of two hypersurfaces in AN times P1 and you project it to AN. And the resultant, so this projection is exactly the zeros of the resultant. So this is zeros of resultant. In particular, since this set is the zeros of some polynomial, it means this space here is closed. And this is quite remarkable because it's saying that the projection of a closed set to AN is actually closed. You may think it's kind of obvious the projection of a closed set is closed, but if you look at the projection of A2 to A1, this isn't actually closed, because you might take a hyperbola, for example, and then this is a closed subset of A2, but its projection to A1 is A1 minus a point, which is definitely not a closed set. So what the resultant is telling you is the projection from AN times P1 to AN is actually a closed mapping. With a little bit more work, you can show that the image of a closed set here in AN is actually closed. And this is a very important property of one-dimensional projective space. We say P1 is a complete, which is a sort of algebraic analogue of being compact. So an important application of the resultant in algebraic geometry is to show that one-dimensional projective space is a complete variety. And more generally, by pushing this a little bit harder, you can show that n-dimensional projective space is also a complete variety. Last lecture we were looking at the question of what are the invariants of A3, which is z modulo 3z, on the ring of polynomials in three variables x, y and z. And we got as far as showing that it was k generated by E1, E2, E3, the three symmetric functions, and delta, where you remember delta was x minus y, y minus z, z minus x. And we had to mod out by delta minus some polynomial in E1, E2, E3, and we have now shown how to work it out. It's just the resultant, sorry, not the resultant, the discriminant of E1, E2, and E3, which we've more or less shown how to work out before, at least if E1 is 0. We cheated slightly by setting E1 equals 0 to make the calculation easier. Now, this expression here is an example of something called a syzygy. So syzygy comes from the Greek, where this means together and this sort of means yoke. So if you've got two oxen ploughing a field, they have a yoke joining them together. So a syzygy is something that kind of joins things together. And this particular syzygy is kind of relating these invariants you've got. In general, if you're trying to work out a ring of invariants, we know by Hilbert that the ring of invariants is going to be finitely generated by various invariants, I1, I2, and so on. But in general, we need to quotient out by various syzygies. And then things get more complicated because syzygies need not be independent. These would be sort of first-order syzygies, and there might be second-order syzygies giving you relations between the first-order syzygies. And there might be, of course, third-order syzygies giving you relations between the second-order syzygies, and so on. So it gets to be a real mess. I'll just finish by giving you an example where you have some more syzygies with relations between them. Suppose you just take the ring Z over NZ acting on the ring of polynomials in two variables by taking x and y to x times zeta and y times zeta, where zeta is a primitive nth root of 1. Then it's not too difficult to work out the ring of invariants. It's generated by x to the n minus 1y, x to the n minus 2y squared, and so on up to y to the n. And now, if we call these elements, let's call them an minus 1, an minus 2, and so on, you see there are actually lots of relations between these. For instance, we have an minus 1 squared is equal to an minus 2, and an minus 2 squared is equal to an minus 1, an minus 3, and so on. So we get lots of syzygies between these invariants of this group action. Okay, so I guess that's about it for resultants. The next lecture will probably be on something to do with formal power series rings.